turbofans make a lot of noise. You know, those engines on airplanes, they're like 120 decibels. They're noisy, and that is one of the main reasons why airports are located quite far away from civilizations usually. And turbofans are turbo machines, and ones that spin really fast. In fact, some turbofans can spin up to about 100,000 RPM. While that is on the high end, even regular turbofans on passenger airplanes are around 3,000, 4,000 RPM. So because of their very complex operation, the questions become, why do they produce so much noise, and where is this noise coming from? If we knew where the noise was coming from and why, we could do something about it and make airplanes far less noisy. So the flow structures coming off of the blades in the turbofans, whether they are on a compressor or turbine, are strange and numerous. Which ones produce noise, which ones aren't, that is, and what frequencies, those are the questions we'll be looking at today in this podcast. And to do that, we're looking at a paper called Identification of Noise, let me zoom up actually, here we go, Identification of Noise Sources in a Realistic Turbofan Rotor using Large Eddy Simulation, and you can find this link in the description below. So the title gives us a clue as to how these researchers are going to try to determine where the noise is coming from and why, and what is this LES, why they're using this large eddy simulation approach. And I'm going to say that in this podcast, we will see, in my opinion at least, the best CFD that we have seen for over a year in this podcast series. So like if you take all the podcasts that we've done over the last year or so, this CFD presented in this paper is, in my opinion, the best. And we'll be covering the results of this a little later on and why it is so good. But first, let's talk about CFD and noise, or aeroacoustics. And the reason why is because it's quite interesting. So trying to identify noise sources using CFD in general is really a very difficult task. In fact, I personally know quite a few capable researchers who didn't pass their PhDs simply because they weren't even able to get moderately accurate noise results from CFD on airfoils. That's how difficult it is. And the reason why is because noise largely comes from turbulent structures, and no CFD approach that is used today, at least in modern times, resolves all turbulent structures. So you start off with RANs, which is about as accurate as a kid drawing a picture with a crayon. Then you have URANs, which is a little bit better. Then DES, which is even better again. Then LES, which is definitely a step up. But even in its name, we are told that we are not really looking at anything other than the large eddies. And we know that in terms of how much energy is in the spectrum, the large eddies contain the most energy. But still, they have small eddies that have a little bit of energy, which does contribute to turbulence and noise production. And in LES, we are not resolving these structures here. So it's not going to be 100% accurate either. So going to finally DNS, direct numerical simulation, we do resolve all the turbulent structures, but we are nowhere near close to being able to use DNS for any practical application, even like something like a turbine, or let's say one stage of a turbine, or even one blade of a turbine. And the reason why is because to use DNS, even for like one blade, you would need something like 1 billion cells or more. And to do like a regular turbine, you'd need to have billions, maybe even tens of billions of cells. And currently we're at around about 200 million to about 1 billion cells is where the industry standard is today. And to be perfectly honest, at the rate that we are going, I doubt that we will ever be able to use DNS for any of these applications. And I don't mean like in our lifetimes, I mean like ever, like not even in 1,000 years, because of our current way of doing things. So let me explain what I mean when I say that. So in industry, how we do CFD is that, let's say we want to simulate a golf ball. So you look at how many cells you need, and let's say you want to start by looking at 10 million cells. And if you run a 10 million cell mesh simulation on a one core on your computer, it will take a while. You might have the option of using a number of cores instead to speed up the process. So you pick 10 cores to use, because if you were to run this simulation just on one core, let's say it takes 1 month, but if you use it on 10 cores, it might take 4 days. Now note that I said 4 days and not 3 days. So you're using 10 times the number of cores. So why wouldn't it take only 1/10 of the time, i.e. 3 days? The reason is because the mesh gets divided up among the cores. But the cores have to share information about the cells in their region that they're solving with other cores in other regions. So let's say you have your regular domain, and you've split up to 10 regions. Each core takes one of those little regions, and then it's to share information across these borders to be able to solve those other regions. And that takes CPU power. It's like a middleman. So just shuffling information around, you don't have 100% efficiency now. So you need to spend more CPU power to communicate between cores. Now, losing maybe 10% efficiency isn't too bad. I mean, you still get your simulation in 4 days instead of 3 days, and that's good. That's a good trade-off in industry. But what happens when you go to 100 million cells? Now, if you were to run this 100 million cell mesh on a 1-core computer, it might take 400 days, and that's not practical. Like, you can't just say to your boss, oh yeah, I'll have it to you next year. Like, unless you're in December, next year isn't going to be soon enough. So 400 days to do one simulation is not going to work. So you say, well, I want it now while I'm still young. So let's run this on 100 cores. So instead of taking 4 days, which would be 1/100th of the time, it takes 10 days because now you have 100 cores, and all they will need to share information, communicate with each other. That takes up a lot of CPU power. So this CPU power isn't directly solving anything. It's just passing information around, and that is the middleman. So because we have jumped to 100 cores now, the inefficiency has grown. Perhaps it's 30% inefficient now. So 70% efficient, 30% inefficient. But still, you get your simulation within, like, let's say a week or just over a week. So you can still do your job. You can like solve problems. You don't have to wait until next year to get any answers, and you probably would have forgotten what you're doing by then. But anyway, let's say we are now simulating something that requires 1 billion cells. So using just 1 core might take you 20 years. So that obviously isn't doable. So you decide to use 1,000 cores. And instead of taking 7 days, which is 1/1000th of 20 years, it takes 200 days. The inefficiency has grown a lot because now you have 1,000 cores all passing information around. That's a lot of middleman work. So 200 days doesn't work for you, so you decide to double the number of cores used to 2,000 in an effort to get it sooner. And it works kind of. You knock it down to 140 days. That's not 100 days, that's not half, but it's better than 200 days, it's 140 days. So you decide to double the number of cores again to make it 4,000 cores to get it sooner, and that knocks the time down to 130 cores, so 130 days. You've literally doubled the number of cores, but only dropped the completion time by less than 10%. So you say, well, I need it sooner. So you decide to use 1,000 cores and double it again. But the completion time is still 130 days. It hasn't changed at all. You've doubled the number of cores, but made no difference to the completion time. At this point, using more cores does not make your simulation run any faster because there is so much overhead with the amount of data that you have to pass around between the different regions and different cores that just eats into efficiency and makes it no more efficient it actually makes no more inefficient when you run it with more cores. And in fact, in practice today, around 3,000 cores is the upper limit, where above this, we don't actually get our simulations solving any faster. This is the point of diminished returns. So what that means is that we cannot solve a 1 billion cell simulation in less than 130 days, no matter how many resources we throw at it. And this is just a general thought experiment. 130 days might be for one simulation, another simulation might be different, and the reason why is because depending on what terminus model you're using, what mesh you're using, if you're using a dynamic mesh, for example, with it moving, that takes longer to solve than one that's static. So if one type of simulation, 1 billion cells might take 30 days, and that's the best we can do. Another simulation might take 130 days, and that's the best that we can do depending on what the mesh is doing, what the simulation is doing. But anyway, let's say we go to 2 billion cells, and it might take 1 year to solve instead of 130 days. And if we go to 10 billion cells, it might take 10 years to solve. And that is using a supercluster of thousands of cores, a very expensive and large resource tied up just for one simulation for 10 years. So practically speaking, we might be limited to maybe 500 million cells or just 1 billion, depending on the CPU power in today's industry. And that's about where we're at now. Well, CPUs haven't been getting that much faster, at least not the ones that you can buy readily to make your 4,000 core supercluster or without insane levels of cooling. And there are reasons for that based on like the architecture and like how thin we can get the wires, etc. That's just another topic, but generally speaking, the CPUs haven't been getting that much faster at all really lately. So we're limited in terms of how fast the CPUs can be. So the only way forward is to use more cores, but as we've just seen, more cores leads to more inefficiency, and there's a point where more cores won't actually reduce the solving time. So we're limited there too. So let's say we want to do a DNS simulation of an airplane, and that might take 15 billion cells, maybe more. So the only way we can do this is to run the simulation for 20 or 40 years, because we can't use more cores. It's not going to make a difference. Our cores are not getting faster. So that's the option that we're left with. That's not practical, obviously. As such, the current architecture of computers and Navier-Stokes CFD, it doesn't seem like we will ever be able to use DNS. Now that is where lattice-Boltzmann comes into it, which if you don't know what that is, that's a different type of CFD, and its major drawcard is that it is much more efficient when using more cores. But even this approach does have inefficiencies, and the same thing happens over the number of cores that you use with lattice-Boltzmann CFD. And the more cores you use, the less the efficiency is. Efficiency drops. So there is an upper limit to the number of cores we can use for this approach as well. As such, lattice-Boltzmann may not be the solution we're looking for either. So the only current way that I'm aware of that we'll be able to resolve all turbulence for a real-world application like an airplane or a car, and not just a simple flow over a flat plate, is possibly with quantum computing. That is the only promising method I can see, and that is because these computers are registering being like 100 million times faster than the average core on your computer or your cell phone, whatever, which is really impressive. 100 million times faster. So without a major shift in technology, DNS won't be possible in my opinion, ever. So just as a side note, when I was researching quantum computers, I was wondering how fast the human brain was. I was just curious. Now there is some debate when I was looking this up, but the general idea is that what I found was that the subconscious mind processes about 11 million bits per second, while the conscious mind processes only 50 bits per second. 50 bits compared to 11 million bits per second. So that means that the conscious mind deals with like 99.999% of the information we get, and the conscious mind only deals with about 0.0001% of the information we get. That disparity is insane. So our conscious brain power is a real commodity and we need to use it right. For example, when we are doing CFD, we need to make sure we are using our brain and knowledge properly. And if you want to improve how effective your brain is when doing CFD, check out our CFD courses link below, including how to use OpenFOAM as a complete beginner. Anyway, I thought that brain stuff was really interesting, but let's get back to this paper. So where does this leave us with modeling noise? I've already mentioned that it's really difficult to do. And depending on which terminus modeling you use and which approach you use, it can result in being not accurate at all to being quite accurate, and we are limited in terms of number of cells we can use. So the best approach we have from a Navier-Stokes stance is with large eddy simulation, LES, which is what this paper is looking at. And this approach models the large scale stuff, which with the assumption that the large scale stuff produces the bulk of the coherent noise, it should give us a decent approximation of the noise produced by this turbofan, or at least the part of it that they are looking at. So let's dive into this paper to see what they've done. They say that this study aims to identify the noise sources of a rotor only, and in particular only one blade. So that is likely because of what we were just going through. Where to get even a decent approximation of the noise produced, you need to use so many cells and it takes so much time that simulating even an entire rotor currently is prohibitively expensive. So they say that they have used 62 million cells for this setup. 60 million cells, that's just one blade out of dozens on each stage of a turbine. And a turbine has quite a few stages. And then you have the compressor with hundreds more blades and hundreds more in the fans, compressor and turbine. So this is just one blade out of these hundreds of blades through this entire turbofan, and they're doing 62 million cells just for this single blade to get the noise off this blade. This is what I mean in terms of how hard it is to do. So to do an entire turbofan, this would require tens of millions of cells and maybe more, and that is just for LES, not DNS, just LES. And that gives you an idea of just how difficult it is to simulate noise for a turbofan, and really any object. Now, they're simulating this turbine rotor by applying periodic boundary conditions to the sides of the domain of a single rotor blade. So in figure 1 here, we see this blade here, and then they have like this sliver that sort of encompasses this entire blade, upstream and downstream. And then on the sides of it, they have the like symmetry condition that they have, this periodic boundary condition, sorry. So that is supposed to simulate the rest of the blades around this single blade. Does it? I have no idea, because how could you tell when simulating an entire rotor would take an entire, like a billion cells? Anyway, they say that they're running this at 62% of the operating speed of this turbofan. Now, I'm not exactly sure what that means, because they say that this is in relation to the speed that results in the fan producing most noise. But I don't know if it is running at 62% of the speed of the fan that produces the most noise, or if they're running at 62% of the speed, and that speed produces the most noise. I'm not sure which one they mean there. I think it's the former, where the speed that produces the most noise, they're running it at 62% of that. So perhaps that is another topic though. Anyway, they say that from other studies, they can conclude that modeling the trailing edge of the blade is not enough to replicate the noise in a turbofan, or at least on this blade. They say that the tip flow and how that interacts with the neighboring blades is also very important, and that's where we run into a problem there. Like, you need to have other blades around it to be able to replicate this, but then you have the number of cells that you need, and you have this periodic boundary condition hopefully doing that. And just from my general turbo machinery knowledge, I would say that also the root of the blade is also very important, generally speaking, because there can be vortex structures that come off there and create noise. Now, this LES was for compressible flow, which further increases the amount of time it would take to solve the simulation. And what's more, they are using something called the Taylor-Galerkin scheme, which is third order accurate in space and fourth order accurate in time. That alone increases the accuracy of the simulation greatly, but it also increases the solving time. To give you an idea, in general aerodynamic simulations, having a second order accurate scheme is pretty good. That's like, I would say, like the standard in industry. But these peeps are using third order and fourth order respectively. But that is what is needed for noise prediction because of how delicate the structures are and the noise produced. Now, they say that they effectively initialized this simulation for one full rotation past the point where they would say that the flow has been accurately determined, which is quite rigorous of them. They then ran the simulation for 7 more revolutions and collected the data over those revolutions. The time step of the simulation was 1.2 by 10 to the negative 8 seconds, which is, 12 nanoseconds. That's insanely small. And I mean, to give you an idea of just how fine that time step is, when we simulate flows around cars, we usually use a time step of around 5 by 10 to the negative 5 seconds, so 50 microseconds. These geezers are using a time step 3,000 times smaller than that, 12 nanoseconds compared to 50 microseconds. So that would take forever to go through even just one rotation. So that is very rigorous of them, and I'm very impressed with the CFD so far. Now, let's move on to the validation part. So one weakness is that they don't present a mesh convergence study, and I'm actually not surprised because, to be perfectly honest, I don't think you could go much finer than what they had and still run the simulation within like a month. And they don't give the amount of time it took to solve this, but I wouldn't be surprised if it was a month or longer. I mean, 62 million cells isn't that much, but it is compressible, third order, fourth order with a 12 nanosecond time step for 8 revolutions plus initialization. So if we were just to take the 8 revolutions and say that the time step was around 2000 RPM, at a time step of 12 nanoseconds, that means that even without the initialization bit, the simulation needed to run for 20 million iterations. 20 million. That would take at least a month on like 2000 cores, maybe more. So while a mesh independent study would have been nice, I can definitely understand why they didn't do one. I mean, it would take like a year, probably longer. And you can imagine if you had like a small error in your CFD setup, like a year of your life just gone straight down the drain. That'd be really frustrating. But they do have the validation of their CFD in table 2. So let's go down to that table here. So the experimental data given is the mass flow rate, total pressure ratio, and the total temperature ratio. So like how much the pressure and temperature change across the blade, because the blade is compressing or expanding the flow, and that changes the pressure and temperature of the flow. And the LES results are within 1% of all the experimental values, and that is very, very impressive. They have more validation data though, so let's go through that. So in figure 3, we see the normalized mean velocity through the rotor. The top row is for the experiment, so this row here, and the left column is for the axial velocity, so like going into the page. The middle column is for the radial velocity, so like away from the center of the rotor, and the right column is for the tangential velocity, so like perpendicular to the blades. The bottom row is for the CFD, and you might be wondering why the CFD results have multiple blades when there is only one blade simulated. That is just the repetition of that single blade due to the periodic boundary condition they placed on the side walls of the domain encompassing the single blade. So let's compare these figures of the experiments with the CFD. So overall, the CFD very closely resembles experimental data, and that is impressive given how difficult the CFD is to get right. But zooming into the details, let me zoom in here a little bit here. we can see that the extrema, so the maxima and minima for the various velocities don't quite match. So for example, if you look at the axial velocity, let me scroll over there. So we see the red figures here. On the left, the minima in the experiments registers around 0.7, and I think that is meters per second. The maxima in the axial velocity ranges up to about 1.1 meters per second, while the CFD is only around 1 meter per second, so it's a little bit less, it's about 10% less. Moving to the radial velocity, so this middle figure here, the CFD registers lower radial velocities across the entire range, while the tangential velocities, the right column here, the CFD registers higher velocities across the entire range. So this is interesting because on the face of it, you'd conclude that, okay, the CFD is good but not great. There is this difference here. But I want to dig a little deeper because I think the CFD is not done justice in this case. And the reason I say that is because the forces given in table 2 are very good. So the forces here, and quite frankly, far better than the flow vis in data in figure 3 would suggest. And I think I know why the CFD looks worse in the flow vis than in the that is primarily because of the experimental data, not the CFD. So in the figure caption, if we go down here, it says the data was taken in the experimental data by hot wire. And this is potentially a problem because while I don't know what type of hot wire they used, it typically doesn't matter because the same error occurs across almost all types of hot wires. And to explain what I mean, so they took 3 orthogonal velocities, and I am assuming that they used a 3-axis hot wire, but even if they used a single axis hot wire, what happens is that the hot wire might measure the velocity in one direction, but the velocity in one of the other orthogonal directions also corrupts the hot wire's results. Let me explain. So a hot wire is exactly what it sounds like. It is a wire that is hot. And then as the flow goes over it, the wire cools down. As such, the circuit needs to supply more juice to the wire to get the temperature back up through resistance. Knowing how much you need to supply means you can calibrate the curve to determine what the cooling rate is and hence the velocity that the wire is seeing, the flow going over the wire. That is hot wires in a nutshell. Now, the hot wire spans the distance between 2 prongs, and these 2 prongs are what connect the hot wire to the rest of the circuit. Now, you have the wire effectively exposed to 2 directions of flow. Hence, while you might want to measure the velocity in one direction, you're going to measure some of the other velocity as well as it corrupts the flow coming over. And that is what I think is happening here, because I find it strange that the CFD underpredicts the radial velocity across the entire board, but overpredicts the tangential velocity across the entire board as well. That indicates that some kind of systematic error is occurring here, and that fits the idea that the hot wire results are being corrupted by one of the other orthogonal velocities. So I think that in this case, that the CFD is actually a lot better than what we think, and it's the experimental data that is the corrupted data. Another thing too is that the hot wire does take up some room, and I mean that when you say that this point is 10 meters per second, you're not really saying that it's this single point. It's the point at which the entire hot wire is taking up. So if the hot wire is 1 millimeter or 2 millimeters in length, it's that distance that it's taking up is this temperature or this velocity of 10 meters per second or whatever. Now in experiments, that means you have a resolution of 2 millimeters or whatever. In CFD, with 62 million cells, that's going to have a much finer grid. Hence, the temperature readings are going to be much more precise, and we're going to get a much more resolved data, like imagery here. So in other words, the hot wire data is much less resolved than the CFD data, and that is why in figure 5, where we have more experimental and CFD data comparisons, the experimental data is far less detailed. So let's go down to figure 5 here. You can see the CFD is generally a lot more wavy, and there's a lot more differences going on. The experimental data is a lot more like blocky, effectively. So I also think that some of the differences between the CFD and experiments are because of this difference as well. Now, looking at figure 4, so let's go up a little bit. We see some velocity profiles going along the blade from the blade root to the blade tip. At least that's my understanding of what they have here. They say that is the meridional profile. I'm not exactly sure what they mean by that, but I'm pretty sure they mean it's the halfway going through the blade, like that direction. So the axial and tangential velocities look pretty good, so the left and right figures, but the radial velocity of the CFD is consistently underpredicted compared to the experimental data, so this middle figure here. So the authors say here that it may be because of the periodic boundary conditions placed on the domain sides to replicate the entire rotor. That may be the case, but I think that it might also be still because of the hot wire error. So from all the CFD validation and setup information, I'm really impressed with what they have done. I would rate the CFD maybe 8 out of 10 because while there are some potential limitations, like the grid convergence study, some potential differences between the experimental results and the CFD and the periodic boundary conditions, I think the CFD is better than what the authors suggest. And I can understand that they didn't do a mesh independent study or an entire rotor instead of just one blade because of the resources that they had. And this is really the cutting edge part of research. So I think that the current state of our technology capabilities, and this is definitely acceptable, and personally I don't see experiments being able to do a better job here, at least not in such an enclosed space with such a high rotational velocity. And I mean, maybe the experimental technique that could do better than CFD that we have here is PIV with a very high frequency rate. And if you got the cash, but even still, there would be some regions where the laser doesn't get to, and you have quite a few different dead patches going around where there's no data for. So personally, I think that the CFD setup here and the results given are the best you can get right now, which is why I'm rating the CFD 8 out of 10. And if they had a little validation data, which it turned out that the experiments were wrong, then I can definitely see the CFD getting bumped up to like 9 out of 10. It's really good. So let's move on to the results. So in figure 8, we should scroll down here. Figure 8, here we go. We see that the turbulence intensity levels going span-wise along the blade from 25% span, in other words, 25% of the blade root all the way up to almost to the blade tip. So 25%, 50%, 75%, and 90%. As we get closer to the blade, we see more and more turbulence on the suction side of the blade, so these red parts here. This is very important because it is a turbulence intensity that creates a lot of noise. And what this indicates to us is that this region is where a lot of noise is being produced, this tip region. And we will see later in this paper if that is the case or not. So in figure 9, it's pretty sweet, this figures, because we see the criterion being clipped, so we only see the vortices present is what this is saying. And we can see just how many small vortices there are. There are like hundreds of thousands of them. So that's pretty cool. And on the suction side, so the right side of the figure, we see a lot more, especially around the leading edge and blade tip, so around here, this red part, compared to the suction side. And this is telling us potentially where the noise is coming from. And figure 10 shows us another potential cause of noise. So you can see all these vortices, these wiggly worms, exist between the blades, and as one blade rotates through the wake of another blade, that leading edge is even trailing edge is going to chop through these vortices. That creates noise. And this is quite funny because I remember years ago I was talking with this company I was interviewing with. I was fresh out of my PhD, and this company was looking to make flying cars. And one problem they had was the noise coming from the rotors, which would prevent them from being able to operate in urban environments. The noise that they were producing was above the permitted level. So in other words, they're flying cars. If they did produce them, they wouldn't be able to use them in real life. So they asked me how to solve this, and I actually told them a way that works, but they didn't listen. Then years later, I was talking with them again because we'd sort of become friends, and I asked them if they ever tried my idea out, and they said no, and they still didn't know how to fix the problem that they were getting with the noise. So I thought I had given them $1 million idea, and in fact, one worth a lot more than that, but they didn't seem to like it. So, I mean, from a funding point of view, the company was and still is very successful. They recently got like $300 million in funding, more funding, like they've had quite a few funding levels, but they haven't really produced much yet. So it's interesting how funding and production aren't really innately coupled as you might think. But anyway, back to this paper. In figure 13, we see something called the dynamic mode decomposition in the upstream region of the blade and the downstream region. That's a hard term, DMD. What this is showing how much the pressure fluctuates and at the different frequencies. From this, we can get a good idea about the noise produced, because noise is simply just a pressure fluctuation, and the greater the pressure fluctuation, the louder the particular frequency will be. We see that in the upstream and downstream regions, both of these regions, there are 3 specific frequencies with much greater pressure fluctuations than the general surroundings. These are 2.8 kHz, 5.7 kHz, and 8.5 kHz. And these are effectively 3 harmonics from what I can tell. They're multiples of each other. So anyway, in figure 14, we see that these pressure fluctuations at the lowest frequency, 2.8 kilohertz, is coming from the blade root and the blade tip, while the other two frequencies are seen more around the blade tip. So this is to 5.7 kilohertz and 8.5 kilohertz. So in other words, the higher the frequency it seems, the closer to the tip we are, from what I can tell here. So this makes a lot of sense because the blade tip is often chopping through a lot of complex flow, and that leads to impacts with vortices and a lot of turbulence, so that is expected. And at the blade root, as I mentioned earlier in this podcast, a vortex often forms here, and the interactions between this and the blade and the hub create noise. So I'm not surprised that we are seeing that here again. It is quite common. So one way of getting rid of this vortex at the blade root is to create a bulge on the blade's leading edge, which then creates a vortex of opposite sign and cancels out the vortex at the root. I can't remember what this is called though. It's something like a Thomas bulge or something like that. It's something bulge. So I came across it like 11 or 12 years ago, and I can't remember what it's called now exactly. If you know, let me know in the comments below, because I'd be really interested to find out again what that was called. Now in figure 16, we see the sound pressure level at different parts of the blade. Let's go down to these figures here. Here we go. And let's zoom in a little bit so we can see better. Too much. There we go. This is the Goldilocks region here. Not too much, not too little. So anyway, we see the sound pressure level at different parts of the blade, and upstream on the left and downstream on the right of the blade. And we see the legends here. In other words, the left figure is the noise seen upstream, and the right figure is the noise seen downstream. And the downstream noise is definitely greater than the upstream, and we get a few more tonal frequencies as well. So there's a few more jagged parts here. Now the black line is the experimental results, and we can see that the CFD, while not exactly correct, is quite good. Also, I'm not 100% sure which part of the blade this line is referring to. So the CFD results and experimental results seem to be just general representations of each other. They follow the same sort of trends, and it looks pretty good. I'm not sure which one exactly, like is it the blade tip, blade tail, blade root, whatever. But generally speaking, they overlap. So that's pretty good. Now, below 5.5 kilohertz, which is quite a high frequency, and to give you an idea, in most songs, the highs that you're hearing are above this frequency at 5.5 kilohertz, and the lows are around this frequency and lower. And in this region, the noise from the blade tip dominates the spectrum. About 2 or 3 times more noise comes from the blade tip in this region than the rest of the blade, so below 5.5 kilohertz. That means that the tip is responsible for the majority of the low noise you hear from the rotor. So actually these figures that I saw before, where we saw the tip was producing more noise, I think that was for actually low frequencies, not high frequencies. So that clarifies that. So we can see that the blade tip, that's responsible for more of the low frequencies you hear from a rotor and a turbofan. There might be some other components in the turbofan as well, but the blade tips are producing low frequencies here. And above 5.5 kilohertz frequencies, so high pitched noises, the lower part of the blade now takes over and becomes a dominant sound producer. And above this frequency, the lower 80% of the blade produces about 7 dBs more, let's say 7 dB greater sound pressure level on average, which means that the noise is about 4 times louder from the blade root section, like the 80% lower, than the blade tip. So mind you that the lower portion corresponds to the 80% of the blade's span, while the tip is only 20%. So when you think about it, for a frequency of 5.5 or below, 5.5 kilohertz or below, 20% of the blade is producing the majority of the noise. And even above 5.5 kilohertz, sure, the bottom 80% of the blade is producing more noise than the top 20%, but if you were to kind of see how much noise is produced per unit span, that means that the noise is kind of evenly distributed. So what that means is that the blade tip is the main troublemaker here, which makes sense because that is the part that creates vortices and then chops through a lot of the vortices. So in figure 9, let's scroll back up to that figure. So figure 9, we can see a lot more vortices around the blade tip, and they are moving faster. So if you remember that Q criterion on this really cool figure here, you see how many more vortices there are around here, and as we go from the root to the tip, how many more vortices are being produced and being shed off here. And that all translates into a lot more potential for producing noise. And coupling that with a edge that can intersect these vortices, that's a recipe for a lot of noise. So that brings us to the end of this podcast. I really like this one. I think the CFD was really good, but the results were also very interesting as well. For this particular blade, the tip was the main noise producer, and the rest of the blade did have some noisy regions, but to my surprise, the blade root didn't make as much noise as is often the case. So if you like this podcast, make sure to like it and subscribe or follow, depending on which platform you're on. And if you want to get better at CFD, check out our courses linked below, including our course on how to use OpenFOAM from a completely beginner's standpoint. And OpenFOAM is a really good and powerful CFD and free CFD software. And if you want to make your experiments 2 to 4% more accurate, get yourself Amazon Hawk. Most people don't know that their experiments are 2 to 4% in error. And if you want to know why, check the link below to see why. And our next podcast. Peace, amigos.